Hello everyone, I'm here to discuss with you Lecture 15, Resultant of Non-Coplanar Parallel for Systems. The principles were already discussed in the previous lecture series that I have. Now I'm going to present this non-coplanar parallel for systems, and I have four examples for you to listen, to watch, and I hope that you can follow the solutions. So here is the first example. Shown in the figure is the floor plan of the loaded area of a warehouse where sacks of rice are piled up. The rectangular portion develops a pressure of 9 kilopascals, while the triangular portion develops a pressure of 6 kilopascals. Determine the magnitude of the resultant force and locate the point of intersection of this resultant with the XZ plane. So here is the plan, and let's draw the pictorial view, 3D view. So we have here 9 kilopascals on the rectangular portion and we have 6 kilopascals on the triangular portion. Let us denote F1 as the equivalent force on this surface load on this rectangular portion, and it acts at distance 9 meters from the YZ plane or from the z-axis, and of course half of 16, 8 meters from the x-axis. Then F2 for the equivalent loads, concentrated load for the surface load, which acts at 1/3 of 18 is 6 from the z-axis, and 1/3 of 9 is 3 plus 16, 19 meters from the x-axis. So F1 is simply the volume of the pressure diagram. So it is pressure times area over which it acts. So 9 times area, 18 times 16, so 2592 kilonewtons. F2 is 6 kilopascals times the area, 1/2 of 18 times 9, or 9 times 18, 1/2 is represented by 0.5, so it is 486 kilonewtons. Therefore, the resultant force is the sum of these two forces, and it is obviously downward, and its location would be denoted xz and g sub z, while the y value is 0. So we locate the position of r by Varignon's theorem, but first let's solve for the magnitude of the resultant. It is F1 plus F2, so it is 3078 kilonewtons downward. Then by Varignon's theorem, 3078, so it's like summation moment about the z-axis. The moment of the resultant is supposedly negative, but let's just treat it positive. Anyway, all the components will have the same moment as the resultant. So R is 3078, then XZ is equal to the sum of the moments and its components. So it is 2592 times 9 plus 486 times 6. So solving for XZ, XZ is 8.526 meters. Then moment about X, so R times 3078 times z sub z equals F1 times 8 plus F2, which is 486 times 19. So solving for g sub z is equal to 9.737 meters. So therefore, our answer is R is equal to 3078 kilonewtons downward, passing to the point um, 8.526, comma 0, comma 9.737 meters. So that's it for this problem. Now for example 15.2, the second example, for the system of concentrated load shown, determine the resultant force and locate its position by indicating its intersection with the XZ plane. So that's the figure. So first, let's solve for the magnitude of the resultant. So let's draw another figure. these two systems are equal, and we anticipate that the resultant is downward because there are three downward forces and we only have one upward force which is less in magnitude. So R is equal to, let's take downward positive. So the position of R would be xz and g sub z. So R is negative 100 plus 200 plus 300 plus 400. So R is 800 newtons downward. Then we use Varignon's theorem to locate, to solve xz and g sub z. First, we sum up moment about the z-axis. So let's consider this sense as positive as the moment of R. So all downward forces will have positive moment. So 800 times xz, or let's say we use right thumb rule. Okay, we use right thumb rule. So negative 800 times xz. So 100 is positive by right thumb rule about z. Then the rest will be negative. So 100 times 10 minus 200 times 2 minus 300 times 7 minus 400 times 8 because this is 2, so 10 minus 2 is 8. So minus 400 times 8, so xz is equal to 5.875 meters. Similarly, by right thumb rule, so the moment of R about the x-axis is positive. So 800 times g sub z is equal to, of course, 100 is not included. So let's begin with 200. So 200 times 5 plus 300 times 3 plus 400 times 11, because this is 1 meter and this is 12. So 12 minus 1 is 11. So solving for g sub z, it is 7.875 meters. So we say that the resultant is 300 newtons downward, and it passes through the point 5.875, 0, 7.875 meters. That's our answer for this problem. So for our third example, the resultant of the four parallel forces, of which three are shown, is a force that passes through the center of the uniform table. If the fourth force is the weight of the circular table with a magnitude of 600 newtons, so determine the magnitude of the resultant R. The table has a radius of 0.9 meters and the upward forces are the support reactions. So in other words, we don't care the support reactions, we only consider the forces. Take note that the table is uniform, so the weight passes through the center also. So in the opposite direction of the y-axis. So the resultant will also be through this center because it is stated here that the resultant passes through the center of the uniform table. So if we draw another table, the resultant passes through that. Also, the weight passes through the center. So it has no moment. The weight has no moment about both, about the x-axis and about the z-axis. So R is equal to F plus Q plus 200 plus, of course, the weight of the table 600. And we first find F and Q to solve for that R, and the resultant is downward because all these forces are downward. So first, we sum up moment about the x-axis equals 0, so Q is not involved. So 200 is positive by right thumb rule, F is negative by right thumb rule. And we don't care about the weight because it passes through the x-axis, it has no moment. Also, the moment of the resultant is 0 about the x-axis. So 0, or R times 0, equals 200 times 0.45 minus F times 0.6 sine of 30. This is 0.6 sine 30 because the distance of F from the center is 0.6 and the angle it makes with the x-axis is 30. So its distance from the x-axis is 0.6 sine 30. Solving for F, F is 300 newtons. Similarly, summation moment about the z-axis equals 0. So the moment of the resultant is also 0. So Q times 0.7, summation moment about z equals 0. Q times 0.7, then don't care 200 and 600, the weight of the table, because their moment arms is 0. They act on the z-axis. Then minus F times 0.6 cosine 30. So Q times 0.7 minus 300 F, as which is solved in this problem, Then moment arm is zero point 0.6 cosine 30. So we can now solve for Q. It is 222.7 newtons downward. So therefore R is F 300 plus 222.7 plus 800. 200 plus 600 is 800. Therefore the magnitude of R is equal to 1332.7 newtons. And that's the answer. You don't need to indicate downward because we are only asked to solve for the magnitude. Our last example, 15.4. The math foundation shown is in the form of a regular pentagon in which at each corner are columns transmitting the forces shown. To ensure uniform soil pressure, of course, the resultant of the five forces must pass through the center of the mat. Determine the magnitude of the forces P and F. So the condition is the resultant must pass through the center of this regular pentagon, which is a mat foundation, so that the soil pressure will be uniform. So the moment of the resultant about X and about Z will be zero also. But the problem is we don't know the moment arms of F about the Z-axis. But if we denote the dimension of the side of the regular pentagon as E, then each of these will be 0.5 of E. So solution, so this is, I'll denote the side as E because this is regular, so 0.5 of E also. Let's express all distances in terms of E. So from F to O to this corner here, this is the radius of the circumscribing circle rather. Let's denote that by R. Then from F to O, that's also R. From O to the 200 kilonewton force, or it is in this corner where the 200 kilonewton force acts, that's also R. So R. The angle here is the central angle, which is, let's call it theta. This is also R, and the entire angle is theta. So because this is an isosceles triangle, this is perpendicular to this side here. So the angle here is bisected, theta over 2, theta over 2. And let's call this angle here alpha, that angle there beta. So before we solve everything, take note that alpha is, because that is horizontal and is vertical, alpha is 90 degrees minus theta over 2. Now this angle here, which is theta, the angle between R and R, so we can solve beta as theta minus alpha. So what is theta? Theta is, of course, 360 degrees divided by 5 corners or 5 sides, equal sides, so 72 degrees. Then we can now express R in terms of E by sine of theta over 2, sine of 36 or 72 over 2 is equal to 0.5 of E over R. So solving for R is 0.85065 of E. Then this distance from center to this horizontal edge as Z2. Then from the figure, cosine of theta over 2, cosine of 36 equals Z2 over R. So Z2 is therefore R cosine of theta over 2. So this is R, then cosine of theta over 2, cosine 36. So Z2 is 0.6882 of E. Then let's solve for alpha, which is, as I said, 90 degrees minus theta over 2. So let's call this distance x1. They are equal by symmetry, so x sub 1, that's also x sub 1. And this distance as z sub 1. So that is also beta. So alpha is 90 degrees minus theta over 2. So alpha is 54 degrees. Now beta is theta minus alpha. So 72 minus 54. So beta is 18 degrees. So that from the figure, cosine of beta is x1 over r. Cosine of beta equals x1 and r is 0.85065 of e. So x1 is now equal to 0.809 of e. So take note, they are equal in terms of e. So lastly, we compute this distance. Let's call this distance z sub 1 because there is already z sub 2. Then to solve for z sub 1, sine of beta equals z sub 1 over r. Sine of 18 equals z sub 1 over 0.85065 of e. So z1 in terms of e is 0.2629 of e. Now that we have computed the important distances as moment arms of these forces, we can now sum up forces about the x-axis, and let's consider right thumb rule. P and 200 have the same distance. F and 250 have the same distance about the x-axis, but they are minus. 300 is also minus, then its moment arms are. So quantity P's moment of the resultant about the x-axis is 0, of course, is as stated in the problem. So 0 equals P plus 200 times Z2, which is 0.6882 of E. Then minus F plus 200, their moment arm is G1, which is 0.2629 of E. Then minus 300, the moment arm is R, which is 0.85065 E. So simplifying, cancelling out E, which is common to all terms. So we have 0.6882 P minus 0.2629 of F. Then equals, you combine the constants. So equals 250 times 0.2629 plus 300 times 0.85065, because we're going to transpose them to the left, so they become positive. Then minus 200 times 0.6882, so the result is 183.28. Call that equation 1. Then summation moment about the z-axis. So we have right thumb rule. So F times x1, F times 0.809 plus 200 times 0.5 E, then equals P times 0.5 of E plus 250 times 0.809. Of course, the moment of the 300 kilonewton force is 0 about the z-axis. So simplifying, combining, cancelling out E, so 0.809, 0.5 B minus 0.809 F is equal to 200 times 0.5 minus 250 times 0.809, and that is negative 102.25. So call this equation 2. Now, solving these two equations simultaneously by substitution or by elimination, then we get, that's already algebra, P is 411.8 kilonewtons and F is 380.9 kilonewtons. So I hope that the presentation of the examples are clear to you. This is a matter of um, applying right thumb rule, and this moment of forces about space was already discussed in my preceding videos, lecture videos. And in fact, these are easy because the moment arms are direct perpendicular. And secondly, the forces are parallel. And I hope that you keep on watching my lecture videos. I hope that these videos will help you in your preparation, in your transforming yourselves into better students. And I hope that you will excel in your studies. So just keep on watching until you master all this. So of course, don't forget to subscribe if it is your first time. So bye bye.